We acknowledge the first Australians as the traditional custodians of the continent, whose culture is the oldest living culture in human history. We pay our respects to elders, past, present and emerging, and we respect their cultural heritage, beliefs and relationship with the land. We extend our respect to all Aboriginal and Torres Strait Islander people here today. They share the memories, traditions and hopes of the traditional ancestors with the new generations today and in the future. We would also like to thank them for looking after this land for thousands of years.
Good afternoon, everyone, and welcome to SciFest 2023. This is our final session for day one, and it's been an incredible journey already. There are so many programs going on throughout the week celebrating National Science Week, and of course we wouldn't be able to put on SciFest without support from Inspiring Australia, so thank you to them as well. Today we're going to finish off today literally with a bang with the Fizzics Education liquid nitrogen show. So I will hand you over to Ben from Fizzics Education now and enjoy the show.
Thank you so much, Karen, and hi to everyone. I know some people are watching me on the recording. Hi to you as well, and hi to everyone who is here live with us. I'm hanging out in Western Sydney in Durrow country. My name is Ben. I'm from a place called Fizzics Education that teaches science, lots of it, which means Science Week is kind of our thing. We're very, very busy doing all sorts of science stuff. We got to hang out with Dr. Carl this morning with a couple hundred schools with that. I was doing a science show at another school this afternoon, and now I get to hang out with you and do some liquid nitrogen stuff. So the good news is I like to chat with you guys. It's really, really handy. And actually the best way we can do this is if you look down the bottom of your screen, there is a thing called Q&A. And Q&A is what it says, questions and answers, and which means that I'll have that up throughout. And you might have some questions about liquid nitrogen, maybe changes of states of matter, or maybe some other science question, whatever you might like. And I'll keep an eye on that throughout. Now, I do have a lot of science stuff to do, and I've got a lot of liquid nitrogen to work with. So let's do less talking and more showing you some stuff in our 45 minutes of liquid nitrogen things. So I'm going to do a bit of a different view all the way out to here. This is our place. I live in a padded room. No, I don't. This is our conferencing studio, and we're going to do some liquid nitrogen things. Liquid nitrogen is held in a dewar. A dewar holds liquid nitrogen. It's kind of like a really good thermos for now. Two walls of metal going around, and they suck out the air between the walls of metal, and they make a vacuum. That's a good vacuum. This is a very, very good vacuum, and it's very good at holding liquid nitrogen. It's cold, and we're going to talk about how cold it is soon enough. But now I know that I need to have my glasses on the whole time so I don't freeze my eyes. All right, so I'm going to pour in my liquid nitrogen. Now, if I never told you it was cold, there is a massive giveaway that it's cold. And that's the fog. You can see the fog is dropping downwards, not going up. Now, if you get a hot kettle, boil the water in the kettle, you will see water vapor, which is what you're also seeing. That white stuff is water as a cloud forming around here, around the cold nitrogen gas. Nitrogen gas is falling down, the water vapor is falling down because it's cold. But with a kettle, it gets hot, spreads out, and gets lighter than the air around it, and up it goes. Now, we're going to do a lot of experiments with this. I'm not going to wear gloves. I know you may want me to because it feels like it's going to be safe, but it actually makes it safer without gloves. So I'm going to do some experiments to show you why. But for now, let's make my way over here, take a seat, and show you what we're dealing with. Yes, I have stuff on my desk to show you some nitrogen things. Now, when I first blow into this, yeah, it's cold. Now, you might have experienced where you are. I'm not sure where you are. You're right across the country, I know. But there'll be some people where it's really cold. When you breathe out in the morning, you get fog like that condensation. Now, as you breathe out right now, water is coming out of your lungs as a gas, and you can't see it. But when it's cold enough, the gases clump together, form little liquid droplets, and you make a cloud. So how cold is this stuff? So rather than just saying a random temperature, which doesn't help us much, we're going to compare it to temperatures that you know. So I'm going to briefly share my screen just for a moment and give you an idea of how cold this stuff is. So it'll come on up, so it goes bloop, and up we get to see it. There it is. Now, Sydney today is not quite 21 degrees Celsius. It's a little bit cold on that right now, but that's like an average sort of a day. It's actually a bit wet in Sydney right now. There's a bit of a storm cloud over us. Now, we do actually teach all over the world, so we do teach into America. That's why we've got the Fahrenheit on the right-hand side. But most of us around the world use Celsius. So it's 21 degrees Celsius on an average day in Sydney. Now, you would know that you have other temperatures, like in your fridge. Your fridge is 4 degrees Celsius. It keeps your orange juice cold. The stuff I'm using today is way colder than that. Well, if you think about what other temperatures you might have, well, we could have 0 degrees Celsius. 0 degrees Celsius is when you have water freezing. Water freezes at 0 degrees Celsius and then turns from a liquid to a solid. Weirdly, it expands. Most materials don't do that when they freeze, but water does. But 0 degrees Celsius, water freezes. So what about in our freezer? Our freezer at minus 18 degrees Celsius. It'll freeze your meat. It'll keep your ice cream cold. And yes, I do actually make liquid nitrogen ice cream. That is a thing, but not today. But we do actually make liquid nitrogen ice cream on special events. But we're dealing with much colder than our freezer. Let's go even colder. The coldest day ever recorded, ever, was minus 89.2 degrees Celsius in Lake Vostok in Antarctica. That's crazy cold. Now, if you think about it, that's the coldest day ever recorded, which means if I go a temperature below that, you're dealing with temperatures that are not natural on Earth, at least never been recorded anyway. And liquid nitrogen is very much the case that. If I drop on down, that's what I'm dealing with. I'm dealing with minus 196 degrees Celsius stuff. That is very cold. So I'm going to stop sharing for a moment. It is cold stuff. I mean, when I blow across it, water comes out of my mouth and then it turns into a condensation cloud. But we're going to see a lot of freezing happening as well. So I'm going to make sure our Q&A is set up so I can see your questions. Feel free to ask questions throughout. I do keep an eye on it the whole time, but let's do some science with this. So first job, I have a milkshake cup, and when I pour our liquid nitrogen in, I'm going to zoom in on our camera, and I want you to keep an eye out about what the liquid does. So here we go. I'm going to go in close as we pour it in. Here we go. Now look, I know it goes a bit blurry, but look. Interesting. Bubbling away. The screen has been, you can see it all bubbling away, boiling away. Now, if I come back to me, it is very cold. Now, Karen, while you're in the room, I did get a message here from a Karen, so I'm guessing it might have been you. It says I'm not visible, but I believe I am. So it might be if you could just chime in and just let me know. But I think we're okay. Anyway, we've got here, for those people who could see, we have it boiling away.
I can see you fine.
You can see it's fine? Okay, so it confused me because we had another Karen. Cool. All right, so if it is for you, the person who wrote that in, there's likely a local issue, so that because Karen, who's helping us in the background, could see me, you may want to just check your cables or something on your monitor or TV. Thanks so much, Karen. Awesome. Okay, so back to this. I thought maybe I had a local issue in our spot. Sometimes it can happen during a storm, but we're good. All right, so we saw the boiling. Liquid nitrogen boils at minus 196 degrees Celsius. It boils. At minus 196, hang on, water boils at 100. But we're not dealing with water. Water needs a lot of energy to separate into gas molecules that can then move around. Liquid nitrogen needs very little, heat to separate and turn to a gas. So let's actually show you what it's doing. If I get a glove and stretch it and place it over our cup, oh look, out we go. Well, our nitrogen is spreading out a lot. In fact, liquid nitrogen gets over 600 times bigger as it boils. And you can see it just keeps on getting bigger and bigger and bigger and bigger. And that is the real danger of liquid nitrogen. It spreads out. Now, that is a stretchy glove. What I'm going to do is put it into something that's less stretchy. That's why I have my coffee here. Now, as an educator, we very much, like many educators, we drink a bit of coffee. And we use our cans a lot for some experiments. So let's put in our liquid nitrogen into our can. And remember, it gets 600 times bigger as it boils. What might happen if we put our nitrogen in and then put the lid on? Throw it in the Q&A. What do you think might occur? Should be easy to predict. So I'll give us 3 seconds for that, see if anyone mentions it. Looks like it is, here we go, dropping it down. The lid will pop off, it will pop. A lot of people saying pop. Now, I like how Emily said nothing. Now, nothing is a possibility. Nothing is an answer in science as well, but lots of people going for pop off, blow up, explode, stretch the can. All right, let's find out. All right, I'm gonna clip it on and let's see. Ready, 3, 2, 1, clipping on. Yeah, it does, it pops, it explodes. And actually, what you just saw is the real danger of liquid nitrogen. This container, this dewar, has a lid which is loose, completely loose. If it wasn't loose, we could risk an explosion with this particular type vessel. Have a look here. I'm going to go all the way over here. See this? That's our pressure release valve. It actually protects us in case there's a problem with the container. I'm going to just clip this on again because I can. So I'll clip it on again. You can see again, I've only poured a small amount in, and yet when I go on clip, it builds up pressure and off it goes again. It is explosive. So let's show you what is going on. Let's do a really quick drawing of our dewar. So a simple drawing of a dewar. We have there's a side and it goes around, there's a side and it goes around and around we go. If we chopped the dewar vertically, it would have a shape kind of like that. And inside there is nitrogen. So I'm going to draw that. There's my blue for nitrogen, that'll do. So N2 if you want to be scientific, the nitrogen's joined together as two atoms joined together. Now that is constantly simmering. Gas is being formed and it's getting out. Now the dewar has a cap, so there's the cap, but the cap isn't a seal, which means the nitrogen gas can get out safely. It's not a big deal. Now, what if that inner wall breaks just there? The liquid nitrogen would leak in. So in it goes, it leaks in and then it fills in here as a liquid in between the two walls of metal. There's the problem. Because now you've got gas which is expanding outwards, getting over 600 times bigger as it boils, the dewar would explode. Which means you need a pressure release valve to stop that happening in the first place. So there is a valve like that that is designed specifically to let the gas out. The danger of nitrogen, liquid nitrogen, it's not the cold. It really isn't. Now, if I go back over this way for a moment, I understand that it can be concerning that I'm not wearing gloves, and we've heard a lot of the movies and TVs talk about how cold the stuff is. It is cold. It's minus 196 degrees. However, I am more concerned about coffee, tea, hot Milo. Because hot Milo, hot tea, hot drinks, if you spill it on your arm, you'll burn. And yet you'll never see people wear gloves holding coffee, unless it's a cold winter's day. You won't see them wearing gloves to protect them though from the hot coffee, and yet the hot coffee or tea or hot Milo or hot chocolate goes on their hand, they burn. This is not boiling water. It has something going on. It boils at minus 196 degrees Celsius. Let's show you what it would do if it touched my hand. So I'm not going to go pour it on my hand. I'm not silly, but I want to show you a surface that will act a bit like my hand as if it touched my hand. So I'm going to change my view. Now my view is like this. changes over, and I've got myself an old baking tray. And I'm going to pour our liquid nitrogen into our tray. In we go. Small amounts. Now look what's going on. It is sliding and sizzling and moving around. It is boiling incredibly quickly. It's moving so fast because the gas gets trapped under the little droplets and it acts like a little hovercraft. This is called the Leidenfrost effect. The Leidenfrost effect talks about liquids boiling so quickly that gas gets trapped underneath the droplets and it slides. It wasn't really touching the baking tray as much as it looked like it was. It was raised up off the baking tray. So I'm going to bring this back to my face. So I'm going to change my view to me. So, hey, I'm here. And we'll do a really quick view of what would happen if it touched my hand. So over we go. We'll get rid of our dewar really fast. And I will jump onto the Q&A and see if any questions are coming in. But for now, let's draw my hand. So I've got my hand there. Around we go. Round, 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 round. That'll do. One hand done. So if I get my hot coffee, so H2O, but hot, if it touches my arm, everywhere it touches, it'll transfer heat and you get a burn. Just there. That would be bad. You don't want boiling water on your arm. That's how you hurt yourself. Don't do that. That gets hot. But I'm not dealing with water that boils at 100 degrees Celsius at sea level. I'm boiling with liquid nitrogen that boils at minus 196. My hand is not minus 196. Inside your core temperature, you are 37.5 degrees Celsius, give or take, around your heart. Around your hands, you're about 36, maybe 35. You're warm here. That means you're over 200 times warmer than its boiling point. So we're not dealing with water. We're not dealing with H2O. So we're going to rub out that. We'll fix our arm up a little bit. What if we think about the nitrogen? The N2 nitrogen, when it touches my arm, it quickly, rapidly boils, and it kind of forms a bubble. And gas gets trapped underneath it, and it slides on that pocket of gas. It's a boundary layer. It protects me from the cold. And it slides straight off. So now let's have a think about the gloves. Think about it, just logically. We're wearing the gloves because it feels safe. But if it touches it here, think about where it's going to go. It's going to go straight into my glove. Now it's pressed against my skin, and that's how you get hurt, because it's pressed against your skin. That's how cryogenic burns have happened. Now, I could wear long sleeves, right? It could cover the gap of my glove, and it wouldn't go in my glove. But then I'm holding liquid nitrogen with these big fingers where I could easily drop it, frankly, on me. And that's not so good. I have more dexterity. I can use my fingers better this way. And if it touches my hands, I'm not worried because it'll go up my skin and slide away. It's not actually a drama. The true danger of liquid nitrogen is that it's explosive and it expands. So how about we go up and show you what I do to keep us alive? Up, 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 up. Ooh, you're like going, the dude's showing the ceiling. Why would he show the ceiling? This is important. I need that. In fact, not only do I need the air conditioner, I have a little window open as well, because it gets 600 times bigger. It pushes away breathable air. I like to breathe. You like to breathe. We need oxygen to survive. And the deaths, and sadly, there have been deaths. The deaths have come from using liquid nitrogen in the small space and it pushing away breathable air, and they no longer have oxygen to breathe and they don't realize it and they fall asleep at their desk and they don't wake up, sadly. That's just the reality. It's not about the cold, though I can use the cold to do some fun things. Now, how about we show you that it's explosive, and then I'm going to have a look at some of the questions that have come in. So I'm going to get a bottle and we're going to pour in minus 196 degree liquid nitrogen, and we're going to blow something up. Now, I'm not going to blow up the bottle. In fact, our job, we go out to schools all the time. We see hundreds of schools every year, and we do an experiment which involves blowing something up like this. But this room is just not big enough. It's honestly not. But I can get a balloon and we can trap it. Now, when I put this on, it sort of slowly traps the gas. Now, if I take it off, let's see just how much gas can come out of it. What if I get my water, pour it in, and it's just water from a tap. And what we could do is put this in. Let's have a little look and just see what happens. We'll go out and look. Up it goes. Really quickly goes up. It expands over 600 times. So the water transferred heat into it happened really quickly. Let's put our balloon around it and this time trap that gas and then put this into here, and it's going to happen rather fast. This is not for show. This is rather loud. I'm not pretending. It's going to be loud. Now, your monitors, your TVs, wherever you are watching me, it's only going to have the volume of which you've turned it up in the first place, which means it can't get loud for you. It's not going to happen, but it will be loud for me. So, because I don't have like something modulating anything apart from this into my ears. But in we go. Now it boils fast. Faster, 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 faster. Oh, it's building up pressure. Oh, wow. It's about to, wow. Oh, wow. It's really, really, really building up big pressure. Oh my gosh. Whoa. Bang. And look what's happened. It's completely shredded the balloon. This is the danger of liquid nitrogen. It is explosive. And my friend Karen in the background from Virtually Schools Australia were chuckling because it's also not great for microphones either. And there's one in my room. Anyway, so yeah, it explodes up. So I might just think I might briefly have a look and see what people have been saying in the Q&A. Now, yeah, so Ryan, yeah, a good question, Ruby. Ruby has a great question to me. Ruby asked, even though it won't burn you, will it feel cold? And actually, Emily sort of asked that in the same way too. Your temperature receptors in your skin were never really adapted to handle this temperature. I mean, this temperature is far lower than any temperature that's natural on Earth. It actually feels closer to, you know, when you, I don't know if you've ever done this, but you know, when someone's cooking like in oil, like they're making pancakes or something, and a little bit of the oil spits up and touches you, it feels closer to that if it sits on your skin. It feels more like a little bit of an oil, not quite a burn, but it certainly feels, it almost feels hot because you can't really register how cold it is. Everything around here feels cold. I mean, look at this. There's ice here. Look at this. Heaps of ice. Lots of it. In fact, so it doesn't melt everywhere, I'm going to get some of that ice off my table so it doesn't get totally wet. But you saw all that ice. I mean, the ice is going to feel cold, but this is really, really cold ice. And there comes a point when your hands just can't handle that temperature. All right, so very, very good questions there. So let's keep going. Liquid nitrogen boils, it expands. In fact, when chemicals boil, when they go from a liquid to a gas, they expand, they get larger. Let's explore what happens when you cool certain substances down. So what I think we might do, actually, I might grab my tray again. I'll pop our tray here. Let's get liquid nitrogen and place it around a balloon. What might happen? I'm going to keep an eye out on the Q&A this time, see what you guys think. If I blow up a balloon, oh, done. So we got air bouncing around like it's a whole bunch of kids in a jumping castle. Inside that balloon, the air is bouncing everywhere. It's holding the balloon out. What might happen to the balloon if we cool that air down to minus 196 degrees? All right, we're getting some answers here. Here we go. Pop is one answer. Oh, I got carried. Let's see, the balloon will explode. We've got another one thinking it might burst, might pop. Crumple is another answer. So we've got a few answers here. Some will think it's going to get bigger and explode. Others are thinking it might crumple up. A lot are going for pop. Go boom. Fair enough. It'll bounce. Interesting. All right, so let's find out. So I've got my tongs to hold the balloon. And let's cool this down to minus 196 degrees. Now, it's a bit easier to see if we go nice and close. Down we go. So we can see it really well. There we go. Let's pour our liquid nitrogen over our balloon and let's see what occurs. Over we go, over we go, over we go, over we go, and oh, there we go. Yes, crumple was the answer. Well done. It does get smaller. You know what we can do though? What if I bring this up to my face again and I bring this up to me and warm it up? And we're back to normal. Why did that work? What are your thoughts? So I'm going to keep an eye out on everyone here and see what they thought. So we got lots of people saying it cooled down. Yes, it did. That's true. And the air went inside. It did cool the gas inside. Why did the balloon get smaller? What's your best guess? What do you think? Now remember that the gas right now is bouncing around like kids in a jumping castle, holding the balloon outwards. It has energy. It has a reasonable amount of air pressure. So when we cool down our air, it actually means that it loses pressure. It loses energy. It doesn't bounce around as fast. It has less pressure, less energy, so it doesn't bounce as much. And so the air around the balloon is able to crush it. And that's why it got smaller. Now, when I blew on the balloon, it heated up the gases inside, and so they bounced up and down a lot more, and they built up energy, and it pushed the balloon outwards, and so it stayed out. That's why it worked. All right, so let's do some more with this. Now, let's do another quick experiment around another material. I mean, this is a balloon, and it's rubber, and there's air in it. Now, I have another balloon, a tennis ball. Now, I know it's like, dude, it's a tennis ball. But think about it from a perspective of the materials themselves. Rubber, rubber. Air inside, air inside. A tennis ball is really just a thick rubber balloon. It's got yellow felt on the outside, but it's still effectively a balloon. Now, let's cool our balloon down to minus 196 degrees. Now, so you can see honestly what's happening, I'm going to change my view again so you get to look at my another desk, because you're just going to have to. But there is my ball. We're going to get our ball and we're going to put it into a container like that. I'm going to bring this over here so you can honestly see it. There we go. And I will say that it gets a little bit blurry when we pour our nitrogen over it, but as I do, keep an eye out on the size of the tennis ball. See if it gets smaller. It does. You can see it. It's only little, but it does get smaller. Totally does. Now, remember it's thick though. There's rubber in there, and it's thicker than the balloon, so it's harder for it to compress and get smaller and smaller. But I did do it. Now, we'll just keep sort of turning this for a while. Will the tennis ball remain bouncy? Let's find out. So I'm going to change my view to, me. And I'm going to get the tennis ball. So grab it over here. There it is. Oh, crack. Now let's go down and look at the floor. There's a reason for it. Let's go look at the floor. Because I'm going to bring my tennis ball over here. There it is. And I've got myself a hammer. Let's belt it and see what happens. Yep. Completely crunches it. In fact, I can. And your old camera shakes around as well when I do it. I really am stomping on it. And it crunches it. Look at this. Now, it is a bit blurry when I do that because it's a bit too close on the focus. So let's bring ourselves up to my table again and let's have a look at what it looks like. Look at here. It's crunched. Now, the yellow felt protects my hands from the extreme cold of the rubber, so I'm able to squish it. But it's shattered. Now, I can't blow on it because it's broken. All the little bits of rubber have busted. So blowing on it just warms it up. It's not going to magically go back to a balloon like it did before. It's not going to inflate. This didn't get broken. This did. It does show you that certain materials become brittle. They get easily broken when they get cooled down to very cold temperatures. They go through this glass transition phase. They act almost like glass and they're easily brittle. Now, I might just see if there are any questions that came in through this. It does look like a pancake. I will pay that. A yellow, furry, rubbery pancake. Yes, it does. All right, so let's investigate other materials in the time we have. What about metals? Will they respond to the extreme cold? And my question to you is, how? How will metal change when it gets cooled to minus 196 degrees Celsius? Will it get bigger? Will it get smaller? Will it do nothing? What do you reckon? What are your thoughts? Now, I know there are different types of metal, so what if we just say iron? What would happen to iron when you cool it down? Does it get bigger, smaller, stay the same? What do you reckon? Well, let's find out. How about we go out a little bit and I get a very standard experiment in high school. Ball and ring apparatus. Now the ball fits into the ring, but it only just fits. I mean, if I go nice and close, you can see what I'm dealing with. There we go. You can see it goes in, but it's really quite tight. It doesn't go through very well. It's quite tight, but it goes. So let's get this cooled down. If I use the ball, well, in high school, what we often do is we put the ball into fire and then it expands and then it doesn't fit in the ring. But I don't have fire. I've got liquid nitrogen. So yes, it does. I like this. It will get smaller. Let's see if that's true. We'll pop this in and it boils away. Now at this point, I usually need a tiny bit more liquid nitrogen. And we need this to cool down. So I'm going to change my view and we'll get our liquid nitrogen into here because we do usually need a little bit more at this point. Because we're using a lot of nitrogen throughout this session. And we go. Awesome, that's heaps. Done. Okay. So that's now nice and cold. Let's see what will happen. Let's get our ball and ring together. Has it got smaller? Yes. It's not going through. Metals get smaller when they get cold. Now I've got water here. Remember the water transfers heat reasonably easily? If I put this into water, the metal's going to warm up quickly. And it does so, it's going to change it, yeah? I mean, when it got colder, it got smaller, so we're warming it up in water. Now, if I take it out, you'll see there's ice all over it. In fact, if I chip away at it, there is ice all over the thing. But that's because the metal was way below 0 degrees Celsius, so water froze around it. It doesn't mean it didn't get warmer, though, because that's minus 196 degrees Celsius, and that's probably 20 degrees Celsius. That is like 200 degrees warmer than that. So we get our ball and ring. Let's see if it balances this time. Oh, look at that. Straight through. So the metal ring has gotten bigger. So we're seeing that when you cool down metals, they get smaller, and when you heat them up, they get bigger. And the reason we care about this, it's got to do with, knocked over my candle. The reason why we do this is the buildings, the bridges, the things that you walk into and the structures that we have made, they change in size between summer and winter. They even change in size between day and night because there's different temperatures. Now that expansion and contraction of materials can crack and break them. And that's why they need expansion joints in bridges that can move as the temperature changes. Same thing in some buildings, some modern ones. All right, so let's do some more questions here. Now, I've had a question here from Chang. I love this question. Is nitrogen heavy or light? Now, I probably need to add an extra part to that. That's a good question. When it's cold. So when we cool down, is liquid nitrogen heavy? If we compare it to water for now, it is just a bit lighter, tiny bit lighter than water. So it effectively feels like carrying a thing of water. So there's another thing. As a gas, whilst it's cold, it's heavier than air, so it drops down. But once it warms up, it spreads out, right? And it will rise back up again. But as it's cold, it drops down. But is it heavy? Yeah, it's heavy-ish. If you'd like, you could check the periodic table and you look up its number, its atomic number, and the larger the number an element has, the heavier it is. And nitrogen is 14 off the top of my head on the table, and so it's 14 times heavier than hydrogen, but it's nowhere near as heavy as iron or gold or uranium or one of the heavier elements. So good question. I like that one. All right, so let's do more stuff. Now, how about we use this power of liquid nitrogen and do some interesting things? Let's see if we can get our water again, and we're going to use this expansion of gases to make it do some work for us. So I've got here my bottle. I'll tap away the remaining ice. There we go. We're going to pour in our minus 196 degree liquid nitrogen. In we go. Remember, it gets 600 times bigger as it boils. And this time, we're going to use a lid with tubes coming out of it. Now, let's show you what these tubes look like so you can sort of see what the setup is. So go in nice and close. So you can see I have tubes with blue tack around them, and the tubes go through the lid. So they can let the gas out, but I can direct where the gas is going to go. All right, so now we know the setup. We put this in and around and tie it on tight. So now the gas is coming out of the tubes. Now I need to hold our tubes in the position that I want for a little bit. These are newer tubes, so they take a little while to hold their position. But what we're doing is that we're going to direct the gas outwards, kind of like, well, maybe you can tell me what you think it looks like soon enough. Now, right now, not much is happening. I've got a strong grip on it. My fingers have grip, and it's only boiling sort of slowly, sort of simmering away. Now, remember that water in the pink cup will transfer heat reasonably well. So we're going to transfer lots of heat into the liquid nitrogen, and it's going to boil rapidly. What might happen with a bottle with tubes like that with the shape coming out of it? Have a think, because we're going to find out. We'll put this over here and over here for good reason. On we go. Let's see what happens. In we go. And around we go. Yeah, we made a motor. It boiled rapidly, and when you have gas pushing one way, you're going to go the opposite way. I mean, it's one of Newton's laws. You push one way, you go the opposite way. This did the same thing. If we go in nice and close, so you can see what the setup is, as the gas pushed upwards, or around that way, it'll send it around the opposite way. That's the motion it was doing the whole time. Now, the tubes have to point upwards, because by having the gas going upwards, it then sent the bottle down into the pink cup. If they were facing downwards, it's extremely dangerous, because then it's pushing down, which would then send it up, which is not ideal, because then you got minus 196 degree liquid nitrogen flying around, which is not that great. In fact, that brings up the point. Liquid nitrogen, under the right conditions, used by people that have been spent the time to do the training and whatnot, is fairly safe to work with. But you've got to respect what it does. You still have to think about what it might do. As you can probably tell, this is really not my first day at all using liquid nitrogen. Gosh, I've been doing it for over 20 years. But you'll see sometimes people on YouTube, and worse, TikTok, where they'll use liquid nitrogen because someone's given it to them, and they may not understand what it might do, and it can be extraordinarily dangerous. And some people have been really hurt by this stuff by doing experiments that they don't know what it's going to do and cause dramas. So just be aware that if you can get liquid nitrogen, don't suddenly start doing these experiments, because it's dangerous. So yes, we had lots of people ask, yeah, like it is like thrust. So yeah, we had a question there from Annika. If I put it upside down, it would have taken off, absolutely. Now, here's a really good question I've had from the audience. Ari, thank you. How do you make liquid nitrogen? Well, liquid nitrogen is made by cooling air and compressing it. And as you go through different temperatures, different gases in our air will become, will become liquid. So at minus 196, 78% of air becomes a liquid because 78% of air is nitrogen. It's gotten from the air itself. You just got to cool it down and press on it. Really good question. All right, so let's do a little bit more. We only got a couple more minutes before we finish up. Let's have a bit of fun with this stuff. Mind you, I kind of feel that we've been having fun. Anyway, so I'm gonna put this over to one side. I did have a question in the Q&A about what happens if you rapidly heat it. Let's do that. So I do have a bowl. We're gonna add some really hot water to that very soon. And I've got over here a kettle, like a normal kettle you put on the stove. So I'm going to open this up and put in our minus 196 degree liquid nitrogen. In we go. Now, sometimes when I get our lid on perfectly flat, I'll get fog rings shoot outwards. Let's see if I can get it today. Yay, Karen, we got it again. It's going. Look at how fog rings go. Nice. It's kind of cool. But let's do more than that. Well, if I put this on, there is a valve here that will vibrate when gas passes through it. So if I put this down, sort of makes a very sad sound, like it's not boiling fast. But let's get some hot water here and make it boil rather quickly. So in goes our hot water. Here we go. We can tell it's hot because the steam rises. Steam is hotter than normal air, so it rises. It's less dense. It's spread out. On we go. Sad sound. Now let's make it go more. Boils away. I think my poor little valve has just about had enough. It's going. Boiling away. Now it is boiling even though there's ice on the outside of our kettle. Now the question that came in from the audience was, what if you add liquid nitrogen to really, really hot stuff? Well, I've got hot water. So let's pour our liquid nitrogen into our hot water. Yeah. And now we can watch what might happen. What do you think will happen? Right now we're cooling down the steam that is coming off that hot water. So it drops down, it's cold. But what's going to win, the hot water or the liquid nitrogen? If the liquid nitrogen wins, wouldn't you have a block of ice just there? And if the hot water wins, the liquid nitrogen should boil away, leaving the hot water behind. I mean, what do you think? I'm going to keep an eye out on the Q&A and see what you all think. What's going to win, the liquid nitrogen or the hot water? All right, so let's see. Win-win. Fair enough. Now, I've had a good question come in. What happens if I had no glasses on? I could get liquid nitrogen into my eyes, and what would happen is that the water on the outside of my eyes would likely freeze, and that is not ideal for my eyes at all, because I don't want to freeze my eyes. All right, so we've had some answers in here. A few people say liquid nitrogen will win. Some people, yeah, more nitrogen will win. But you know what? The answer is showing right now. See what the steam is doing? It's going up, not down. The hot water wins. This is still hot. The liquid nitrogen boiled away rapidly, leaving the hot water behind. Liquid nitrogen is not a magical substance that will freeze everything. It can't. It boils away rapidly. In fact, it's actually far easier to cool it down in some ways by putting it in the freezer in some ways. But yeah, that cool it down. So, all right, so we're going to do one more fun thing because we're just about finished. We have about a minute to go. So what if I put this off to one side and we'll do two things, hey? How about I simply just pour it off to one side, not the gas, but not the liquid, but the gas. How about if I put fog and lasers together? If I turn this on, look at this. Scientists use lasers to study clouds, and that's a cloud, so you can see the laser coming on off. So lasers are used in atmospheric research. And finally, because we can, I'm going to get my kettle over here out of the way for this, whoop, and I'm going to get my measuring cylinder. Let's get my detergent because I can, and let's do a semi-trapped version of our liquid nitrogen. Give that a swish, and in goes our liquid nitrogen. It bubbles up, it boils away, and now we've got bubbles, which is kind of a nice, fun way to finish our session. I hope you've enjoyed this time with us on our liquid nitrogen things, and I know that a number of you will have done some stuff for SciFest. So Karen, I hope you enjoyed watching our liquid nitrogen thing again.
I always love watching the show, and I always learn something new and different. And yeah, just remember, everything that starts at the beginning of the week could be useful for some of the quizzes later in the week as well. And what a great way to finish our first day of SciFest. We've had, I think, over about 3,000 students participating in programs with us today, let alone the other things that have been going on for National Science Week. So it's been a huge day of science today. A big thank you for everyone for joining us, and of course from Ben from Fizzics Education for presenting the Liquid Nitrogen Show. So tomorrow we've got the wonderful water quiz at 1 o'clock. Then we have National Maritime Museum talking about Beneath the Sea with rovers. And then actually I'm presenting at 4 o'clock tomorrow afternoon, Mini Beast Magnified. So looking at some of the invertebrates, I'll bring some of my live friends along. And then Wednesday, we've got Geoscience Australia doing trivia. And we have our Careers in Science program at 2. And at 4 o'clock, we have Sydney Zoo talking about innovations in animal care. Thursday, so much science going on. We have another trivia session focusing on planets and space. We have National Maritime Museum back talking about some of the innovations in marine science over time. And then Ben is joining us back at 4 o'clock on Thursday to talk about embedding science into your students learning at home or in the classroom. So it would be a lot of fun and lots of experiments there as well. And finally on Friday, our trivia is going to be looking at molecules and atoms. So our In Their Element session by Ansto will be very useful. That happened at 2 o'clock today. Then we have Street Science doing Moving Forward at 2 o'clock, and finishing off with a really interesting session from Sydney Olympic Park talking about some of their innovations in sustainability at 4 o'clock. So what an amazing week of science. There is lots of on-demand resources as well through Dart Learning on lots of different programs. You can even watch our last year's SciFest 2022 programs as well. So a big thank you for everyone for joining us, and I look forward to seeing you again throughout this week. So thank you so much, everyone.
See you all.
This initiative is supported by Inspiring Australia New South Wales as part of National Science Week, and is proudly brought to you by Virtual Excursions Australia. Thank you for joining us, and we look forward to seeing you again soon.